Okay, we'll start.
Okay.
Okay, good morning, all of you. In the last class, we stopped at this point. Before going to different types of crossover operators and mutation, all these things. Briefly, I will explain all these steps with small example, so that it is easy for you to understand the later problem, how to solve the numerical problem with the minimization or a maximization problem with different equations. So in that we need different types of process. One is initialization, and then fitness, then selection, the crossover, mutation, termination process, all these things. In that, you can see, for example, if you take populations are six, in the six populations, if you take n is equal to six, I mentioned, and the problem or equation may have two variables. Let it be x1 and x2 are the two variables. Then number of bits, either you can take it as a 5 or 4 or 3 or more than that also. We need to fix it that. So now while you are writing the population matrix in the two variables, I make it as x1 and x2, and I represented a number of populations are 6. So 6 rows will get it, and here bit size is 5. Then we can consider each variable is 5 bit size, two variables, 5 into 2, 10. So therefore, 6 rows and 10 columns, we need to get the population matrix. This is the X1 chromosome and X2 chromosome. This consider as a one row or one solution. Like that, we can make it as a six populations. So after getting all the six population, equal bit size, you can use it, or sometimes unequal bit size also we can use it. Because here the bit size I mentioned is a 5, but what is happening for x1? mm, x1 bit size are 5, 6, 7. It is there, the 7x1 bit size. 5 is x2 bit size. So in that case, the population matrix maybe 6 rows, because six populations we have taken, and columns are, and this may be 7 and this is 5, then 12 columns will be there. So that is all depends whether you want to go for equal bit size or unequal bit size. So this is the initialization. And then this initialization, we have to go for as a fitness calculation, and then which one is the better fitness. For that, you have to go for selections, and then again go for crossover and mutation operations that will be followed. Now we can see for that selection, there is a different methods are there. Anyhow, I will explain the different types of methods also. Just for understanding, I am going to explain one method here is a tournament selection method. So what is tournament selection method? The number of members required to be in the mating pool is usually NP, that is a number of populations. Suppose tournament size you select K may be 2 or maybe 3 also. That is all depends on our problem based on the number of populations and all. But preferably we'll take it as a 2 is a size, because 2 will play, 1 will win. Or if you select tournament size is 3, then you randomly pick up the 3 population which is having as a best fitness, and that will be selected in the mating pool. So like that, we can consider here is a k is equal to 2. In that case, we can consider 2 2. Suppose in the, if I select k is equal to 3, then what we can do is, suppose number of populations are 6, randomly you pick up 3 members, suppose fourth, second, and third, and the respective fitness are this one. Suppose fourth row, then second row, then sixth row. Like that, their fitnesses are 27, then 89, then 12. Suppose the problem is minimization problem. Among the three, we need to select the one candidate or one individual. So now how many, if it is a what you call it as a minimization problem, you can select F6 is your meeting pool. You can keep this in the F6 in the meeting pool. And the rest of, again, K is equal to 3, remaining populations you take it. So let it be as a F1, then F3, F5. For their fitnesses, you can write here. And among these three, who is having as a minimum, let it be as a function value, let consider at this point, who is having as a minimum, that you can write it as a, suppose if it may be F3 may be minimum, let us assume that. Suppose maximization case, which is having as a maximum value will come into the mating pool. Like that, we can represent, because our total six population, whether it is a minimization case and maximization case, how many it is going to be win in that point. So like that, we are able to pick up. This is the tournament selection. The measure is, this many populations we may have, and k is equal to 2. 2 we can select which is the best solution. We'll make it into meeting pool. That is the tournament selection. That's what here I wrote here. Best solution will have two copies. Because why two copies? What happening? Totally six population. Let it be here. You can see here totally six populations. In meeting pool, I need as a 6. But if I select the tournament selection k is equal to 2, how many you can pick up among the 6? 2 will select. Which one is the best fitness? That will come for the meeting pool. Let it be 1 and 2 I compared. Maybe 2 is the best one. And 3, 4 I compared. 3 may be best one. And 5, 6 compared. 6 may be best. So how many you got in meeting pool? We got only three, but we required in a meeting pool a number of populations. So what we'll do is, whatever the best solution is there here, P2 two times you can take it, P3 two times, P6 two times, like that. Then the number of populations will remains in the NP only, like that. That's what the meaning here. Best solution will have two copies. Worst solution will never be selected. So worst means suppose one and two, two may be best, one we have to discard. And that is the way we can able to select the best solution and worst solution. Other solutions can have zero times or one copy or two copy, like that. Now you can see here in general scenario, worst solution will not be in the meeting pool. If k is equal to 2, 1 and 2 we are comparing. In that, 1 may be worst solution, 2 may be best solution, 2 will go to the meeting pool, 1 will be discarded. Similarly, if I select the 3, 3 means what? Suppose population 1, 2, 3. We are using as a tournament selection. In that, let consider one may be best. Then what will happen? Worst and second worst solution will not be in the meeting pool, because these two, one is best, it go to the meeting pool. F1 will go to meeting pool, and 3 may be worst, and 2 may be next to worst. So like that. So second worst. So in that case, this two is going to be discarded, like that. If I take it as a k is n, the total population may be 100, and n is equal to, I mean, k is equal to something 5 or maybe 10, like that. Then the general formula will be post n minus 1 solution will not be in the meeting pool. Only the first best solution will go to the meeting pool. This is the tournament selection. Then we'll see understanding before going to different kinds of crossover operation. So what is the normal single point crossover operation? I will explain here. Responsible for generating the offspring. So after getting the tournament selection and all, after selection, it has to go for as a, what you call it as crossover. Two binary strings are chosen randomly because in the population vector, we may have, suppose two variables or three variables, like that. It may be 4-bit binary or 3-bit binary, like that if you take. So you may have n number of populations. In that n number of populations, randomly you chosen first two. That is a parent, let assume that. That's what I mentioned here. Binary strings are chosen randomly from the population to perform the crossover. So let first one or second one or first and fourth or anything or second and fourth randomly you have to pick up the two parents. The some portion of the parent string are exchanged to generate two offspring. Now, what we are doing is here some portion of the uh, what you call it as a chromosome or a population in that, in first population, second solution or second population or anything. So in that I taken, let it be parent 1 and parent 2. Total, let consider as a two variables. In that crossover set, I mentioned as a 3. This is also you can pick up as a random. Crossover site is a random integer chosen between 1 to nd. What is meaning of nd? D is a number of variables and n is a how many bit operation you are doing, or let it be as a the selection process. We can consider crossover site and randomly chosen parents. So let it be from that I taken as a four population. Let assume that in that crossover site is 3. Then after 3 bits, you can see first, second, third. After 3 bit, you can draw a one line and exchange the values. Sometimes some literature they are exchanging this side values, keeping this remains, and some cases they are changing this side bits exchange, and this will keep in remain. At this point, you can see randomly chosen a parents. Now from the two parents, parent 1 and parent 2, now we are going to generate as a offspring. Now what we are doing, bit 3, site 3 is your point. Now after site 3, you are exchanging this bits to this offspring and this bit to this offspring. Now new offspring, we can observe that 1 0 0 is fixed one. Now we are interchanging this two. This one and this one are interchanging. That is only the crossover. Nothing. Whether it is a 1 bit or 2-bit crossover. 2-bit crossover means in between the bits is going to be exchanged. So this is the one point. We can make it 1 and 0. Right. So now we can observe that offspring case, the first 1 0 0 will be remains, and second one we can consider the parent 1 bits is transferred to parent 2 bits is transferred to parent 1. That's what the new offspring is going to be happen. And now, so bitwise, another one you can see that mutation. So like that, we have the different kind of operators that I will explain at the time of different classifications of crossover and mutation operation. This is to understand what is crossover and what is the mutation and all. So now, the second one we can see bitwise mutation. Choose bit 1 to 0 and vice versa with mutation probability. Generally, we can generate one mutation probability. Of course, crossover probability also we can select PC. If it is the randomly you have to generate the PC. Similarly, in the case of PM, that is nothing but a mutation probability is 0.3. You choose and let it be. single solution is involved in mutation, every member in the population can be potentially undergo mutation. So we can each solution it has to perform the mutation. After crossover, you have to go for as a mutation. For each bit in a string, probability for mutation is checked. Then PM is 0.3 and the parent string to be, this is one of string. Now randomly generate the value from 0 to 1, that is R. How many bits are there? That many randomly generate. Let you can consider this is one way. We have different also I will explain. Suppose for each bit randomly you generate one random number between 0 to 1. Now what you have to check after getting these two, we have to compare with the probability of mutation. So now the mutation occurs in the first one, R1. What is R1? It is a 0.2. But what is probability of mutation is a 0.3. But what happened? R1 is less than PM, probability of mutation. If this condition is true, then you have to do the mutation operation. What we have actually, our random number is 0.2, but our probability is 0.3. Random number for each bit is 0.2 and probability is 0.3. So it is a more probability of mutation. So you have to do the mutation operation. What is mutation operation? You have to change the bit. Suppose if 1 is there, make it to 0. If 0 is there, make it to 1. Like that, here is a 0.2. Now the probability of mutation existing is 0, but you do the mutation, you convert it into 0. And then you can see the R6. R6 we are getting as a 0.1 random number, but probability of mutation is 0.3. So R6 is less than probability of mutation. In that case, the value of sixth one, you can see this is 1, 2, 3, 4, 5, 6. One is existing is 0. Then you have to perform the mutation, that will be as a 1. So this is the way we have to perform the mutation. Similarly, if you want to consider the other offspring mutation operation, first write the offspring bits here, whether it is a 0 or ones or like this, and randomly generate for each case of some value from 0 to 1. It may be 0.1 or 0.7 or 0.3 or 0.4 or like that. And probability of mutation, you take it as a suppose something 0.5. This less than zero point 0.5 value, wherever it is there, that values is going to be replaced with the alternate value. Suppose here is 0, you make it to 1, and here may be 1, you make it to 0, and here may be 0, you make it to 1, like that. That is the process we are doing as a mutation. So now what you are doing after doing the crossover and mutation, normal population and offspring population, you mix it, combine that, and you can go for as a best solution, the which is having as a best, or you can say that who is having as a more fitness, that will go for as a next what you call it as next iteration. So this is the way we can able to do in the uh, process. So that is only the procedure we need to go. Now this is all about how crossover will perform and mutation and initialization, then selection, all these things roughly you can understand the sequence. Same sequence. That's what the flow chart also. Initialization, then you go for the fitness, then selection. The selection maybe you will go for tournament selection or random selection, like that we have. I will explain that also. Then crossover, different kinds of crossovers are there. Then mutation, then you go for as a stopping criteria. Whether you reached the number of iterations what you mentioned at the starting point, then if it is reached the total iterations, then you can stop. Otherwise, repeat this process continuously until if it reaches as a stopping criteria. This is the flow chart you can use, or whatever I mentioned in the earlier also, that is also same sequence. The loop will be repeated continuously until it reaches as a stopping criteria. Now we can see some encoding and the fitness value, all these things. So here, encoding of a chromosome is one of the problems when you are starting to solve the problem with a genetic algorithm. That is only the first point. We can see just a minute, 1 minute. Now, you can see encoding of the chromosome is one of the problems. When you are starting the solving the genetic algorithm problem, encoding is very depends on the problem. Like this, suppose we have something like mm, encoding chromosome is the first step in solving the problem. So what we are using, all it may be any number of population. First, we have to represent chromosomes. Each chromosome, it may be n bits. The n bit may be some problems based on the minimum value and maximum value of the variable. We can consider that is a n bit problem. 4 or 5 or 6, suppose if the maximum x maximum may be very large, then you cannot use as a 3 bit or 4 bit encoding problem. Means that chromosome values 1 and zeros, you can make use of a large n bit is required to meet the maximum value. So that is what we need to start with the chromosomes with ones and zeros. Based on your problem, you can decide n bit problem. The process of representing the solution in the form of a starting of bits that conveys the necessary information. So this bit conveys the necessary information, because suppose if you convert that binary to the real value, we can easily identify what is the x value, like that. And just as a chromosome, each gen means this is the first value, second value, all these things we call it as a gen. Each gen controls the particular characteristics of the individual. Similarly, each bit in the string represent the characteristics of the solution. So that is the way these ones and zeros, not normal values, that will consisting of the information about that problem. And then encoding methods, you can see there is a binary encoding. What is binary encoding? Most common methods, ones and zeros only we are using. You can use ones and zeros in each position in the chromosome represent a particular characteristics of the solution. So like that, we can get it as a binary encoding. And another one, permutation encoding. First one is a binary encoding. Another one is a permutation encoding. Usually, in order to use the application like a traveling salesman problem and all, we can use as a permutation encoding. You can see this will be represented as a numbers. So, and then value encoding used in problems where complicated values such as real numbers and where the binary encoding would not sufficient, because very huge problems and all complicated problems, binary encoding will not suit for that. In that case, we'll go for as a value encoding problem. So in that value encoding problem, we have as a something values, the numerical. You can see that where the binary encoding is not suit for solving, we can go for as a value encoding problem. So this is the different kinds of often necessary to develop some specific crossover and mutation techniques for this type of the chromosomes. And another one, last one, tree encoding. Tree encoding is used mainly for evolving the programs or expression in a genetic program. So like this, the chromosome A, chromosome B, like that. For all the cases, we need to represent in terms of the chromosomes only. But the thing is, what we can do, we can able to represent the different kinds of chroma, whether it is a binary encoding or value encoding or tree encoding, like that we may have different kinds of encoding. So it is a tree of the some objects such as functions or commands in programming language. So for that case we can use as a tree encoding. So now the next topic in that is a fitness. As I already mentioned, once the binary encoding or whatever we are using, once the chromosome is defined, we need to find the fitness, because the random population first will generate that population we need to use for finding the fitness. So fitness is whatever the objective function is there, we can find using this population, we can find the fitness value. That's what we mentioned, candidate solution to the problem as the input and produces as a output. So whatever the chromosome you are given as a input to that, and it will give the output. So like this is simply, just for example, if it is real coded, f of x is equal to x1 plus x2, let assume that. And in random population, let assume that real coded x1 is 2, x3 is equal to 3, and this is one population. Second population 1 and 2, and third population maybe 3 and 4, something like that. Then what is the fitness? So f1, the main first population, 2 plus 3, that is equal to 5. This is only the fitness. And F2, second population, 1 plus 2, that is equal to 3. And third population, 3 plus 4, that is equal to 7, like this. So this is the way we are using as a, I mean, what is the input? Whatever the population vector, that is the input, and you can give it to a function that will get it as a output. So that's what input and output. How fit our or how good the solution in the respect to the consideration, and calculate the fitness value is done repeatedly, not only once. Once the random population is there, we are calculating the fitness, and after that we will go for as a crossover and mutation. Then whatever the final solution, again we need to calculate the fitness. So this is the sufficiently fast you can do. A slow computation of the fitness value can adversely affect a genetic algorithm and make it exceptionally slow. And in the most cases, fitness function and objective function are the same. That's what I mentioned. But some, in the real case, sometimes what they will do is fitness is equal to 1 by 1 plus function value, if it is a positive, or something function value is positive, you can use this fitness function, or fitness is equal to modulus of 1 plus function value. This will be as a different kinds to calculate, but in general, a function minimization function is minimum means more fitness will get it. And like that, anyhow, both are same only. The fitness and some function, some problem cases, they will consider same. Any analogy is fine anyhow. And some other cases, what I shown you know, it will be using that formula after calculating the function. You can use that fitness formula, get it as a fitness. And however, More complex problems with multi-objectives and all, algorithm designer might choose and have a different fitness function. As I mentioned, in general, it will you can consider as a function value itself as a fitness and you can proceed, or else we can consider complicated overall and as I mentioned, no different formula we can use it. Now, a fitness function should possess the some characteristics. What is the characteristics? Fitness function should be sufficiently fast to compute. That is the first one. Second one, it must quantitatively measure how fit a given solution is, how fit individual can produce for the given solution, like that. That means obviously if more fitness candidate solution will go for the next solution, next iteration, like that we can able to process. And now, in some cases, calculating the fitness function directly might not be possible to do the inherent complexity of the problems at hand. So, in such cases, what we can do is we do fitness approximation to suit our needs. The following image, I will show that for the example, in knapsack, there is a knapsack problem. It is a simple fitness function which some of the profit values of the fitness being picked. Let it be 1 means it will be picked, 0 means it is not picked. Scanning the elements from the left to right, we have to fill. Now we can see some items, item number 0 to some 6 item number. Then chromosome is like this. What is meaning here? 0 means it's not picked, 1 means it is going to be picked. And profit values is also mentioned and weight values are mentioned. So now in this, they given as a problem, knapsack capacity is 15. Knapsack capacity is 15. Now, what are the elements you need to choose to get as a more profit? It should not be exceeded the capacity. Knapsack capacity is only 15. 15 items only in that bag we can able to carry with their profit values also mentioned. So now we can see what are the 15 means you can see that 1, then 2 plus 1 3, 3 plus 3 6, so then 40 10, then 15. Only these items are the 15 items, let us assume that item numbers if I pick. But in that, what is the profit, total associate profit, which one we are based on the chromosome we are to select. What you can see here is a 1. 1 means you can pick this, the item 1 you can pick, that profit is 9, and this you cannot picked, and this profit will be 5. Then it will be 14, and this will be as a plus 4, then total is 18. Now what will happen if I picked this? It is not possible because total count of that is already only 15. If I consider this, it will go for as a plus 6. 15 plus 6, it is not possible. That's why we are not taking this into knapsack. That's what I mentioned here. Last item not picked, as it exceeds the knapsack capacity. Knapsack capacity only 15. So we need to pick this. So that is the way we can able to use the fitness function and all. Now, basic genetic operators. What are the basic genetic operator? If you remove that, majorly we have is a crossover mutation. But in general, we will start. One is the initialization, then fitness, then the selection, then crossover, mutation, then finally we'll go for as a stopping criteria. These are the basic genetic operators. Now we'll see there are 6 phases of the genetic operator in general: initialization, then fitness, selection, crossover, mutation, termination. So these are the major thing. So if they may ask the question, different questions they may ask, explain the genetic operators, you need to explain like this. Or sometimes they may ask you, explain the different types of crossover operators or reproduction, and or explain the mutation operators or selection operators like that. Or in general, sometimes they ask, they explain different types of crossover operators or different types of mutation operators. So now we'll start one by one. And first one, initialization. So what is the initialization? As you already aware this diagram, initialization, we need to generate the populations. The one solution we call it as a chromosome. In a chromosome, one bit we call it as a gene. So like that, you can generate the some number of solutions that we call it as a total. I call it as a population. This is the initialization. The process begins with a set of individuals with called as a population, and each individual is a solution to the problem you want to solve. That's what each individual, you can see this is a solution to the problem we can known as a chromosome. Now, an individual is characterized by a set of variable known as a genus. So that's already mentioned. Now, so that is what the initialization. We can mention initialization how the population is going to be represented. And second one is a fitness function. So what is fitness function? It will determine how fit an individual is, because we are calculating the input is a population in that first is a chromosome that we have to calculate as a fitness, and then the probability that individual will be selected for reproduction, means for crossover, is based on the fitness score. If the first population fitness is more, then that may be selected, or some other may be less fitness that may not be selected for next calculations like that. And this is we call it as a fitness function. And what is the selection process? As I mentioned in the earlier slides, there is a tournament selection I mentioned like that. We can select randomly, we can have different kind of selection operations also. We'll do that. Selection phase is the fitness individual and let them pass their genes to the next generation. Two pair of individual, let it be as a parents, and are selected based on the fitness score. Suppose we already calculated the fitness and first fitness, second fitness, and which one will be the best, that you can go in for selection process. In that case, a roulette wheel selection and tournament selection and rank based selection. So preferably whatever mechanism also you can use it, or tournament selection also is easy way. You pick up the two populations fitness, which one is the best, that will go for as a uh, next selection operation. Let it be as a mating pool. So like that, or rank based also, based on the fitness value you can give the rank, and you need only best top, you can give the ranks. Suppose I want five um, populations or five solutions, you take it as best five, like that. It is a roulette wheel also we can do, that I will explain. These are the different kinds of selection process. One is a roulette wheel selection, tournament selection, rank based selection. Now we can see first one is a roulette wheel selection. What we can do, each we already calculated the fitness. mm, each fitness you can represent in terms of the pie chart in a genetical. Suppose you can see the chromosome A, B, C, D, and so on, or 1, 2, 3, and so on. We have as a fitness value 8.2, 3.2, 1.4, 1.2, like that. So based on their value, we can draw as a pie chart. Once if you draw as a pie chart, the portion you can see which is having as a more fitness, that will be the more portion, and less fitness, that will be as a less portion. And take it as a one pin in fixed point and rotate this, and wherever it will be, that you can select as a first best solution. To repeat that problem, just spin the roulette wheel and it may be stopped somewhere, preferably which is having as a more space. In that probability will be more to select that. So this is the one way to select as a selection process, because up to 10 populations are there. In 10 fitnesses will calculate, and you can draw as a pie chart and rotate it, and that will be as a wherever it will be stopped, that you can do. This is one way of doing. Fixing point is chosen while wheel circumferences and as shown in the roulette wheel, and the region of the wheel which comes in front of the fixed point, you can choose that. That's what I can consider. Therefore probability of choosing the individual depends on the direction of its fitness, directly on fitness, because if more value is there, more space it is going to be occupied. So therefore while it is rotating, there is a more chance to stop in front of the point. And implementation wise, we use the following steps. Sometimes we can do this way also. Instead of rotating in numerically while you are solving, you can sum that fitness, and you can take it as a probability of that. You can, if it is less than one, and you can individually divide that point and exits that you can able to select. Or easy way is, one formula is there. You just sum the all the values, sum of the probabilities, and we can see this formula. You can use it to select. And population and individuals, we have n populations, and in that fitness value is fx. And what we will do is, probability of selection, Px is equal to Fx by sum of the Fx. So we can, each case we have as a table, chromosome 1, 2, 3, 4, and so on. We have as a fitness, maybe 2, point 2, point 4, or maybe 3, something like this. Then some you can do this, 5 point 6, no? 5.6. This is the sum of the f of x. Now what we have to calculate? P of x we have to calculate. How we'll get the P of x? F of x divided by sum. So f of x is equal to 2 divided by 5.6, and zero point 0.2 divided by 5.6, zero point 4 divided by 5.6, 3 divided by 5.6. And you can consider these values, and which is having as a more value in order, that you can select as a selection process. This is the way we can do roulette wheel selection. And tournament selection, as I mentioned already, whatever the populations are there, you just some fitness values we are having. This is the chromosome A, B, C, D, and so on, something, some number we have. Randomly pick, if k is equal to 2, randomly pick two values and compare it and select that. That is the easiest way. Or you can, k is equal to 3, you can select randomly 3 chromosomes, and in that one we can pick up. So with the best as parent. And suppose if k is taken as a 3, you take the a, e, t, got it as a random selection. What is a value is 5, and e value fitness is 2, and t fitness is 2. Then which is the minimum, I mean here fitness, more fitness, that will be as a 5. You can select that parent for the mating pool. And again you do the random. Suppose that may get something z, s, x. The z value is 9, and s value is 7, and x value is 4. Then maximum is 9, so you pick up as a z is a meeting pool. Like that we can do the tournament selection. This is the easiest way to go for as a tournament selection. That's what I already repeated in the slide earlier while I'm explaining tournament selection. If we have randomly taken as a 3, which one is having as a maximum fitness, that we can select. This is what I mentioned in general. Different kinds, k is equal to 2, 3, 4, and so on. You can take it, and how many it is going to be discarded. That is a mention here. And another one, rank selection. It is very easy because the values are very near. You can see that 8.1, 8.0. If Rayleigh wheel, if you rotate, these all portions are more or less equal in distances, or equal portion, or equal percentage in the pie chart, it will be occupied. But now, how can I select that value with the point? Because more or less, A chromosome and B chromosome are very near, and C chromosome also. If I see that way, can see 8.05 and 8, it is more or less same. That's why we cannot go for relative selection. What we can do is rank based. So just to make use of what you call it as a ranking. Suppose which is the highest fitness, we give the rank one. Then next fitness rank two, like that. And the best rankers you can select. This is the what we are doing in the rank selection. That is only the thing. 8.1 is rank one, and 8.05 is rank two, and so on so forth. Because highest fitness will be the more rank. And how many you want to select? Suppose I want three, you can select as a first three. I mean best three. Rank one, rank two, rank three. You can select instead of you want, you can arrange the order, rank order, and then you can select the A chromosome, C chromosome, and E chromosome, like that. So these are the some of the basic genetic operators. And next one is a crossover operator. So what is the crossover operator? As I mentioned in the earlier also, this is the more significant in genetic algorithm. Each pair of parameter to be mated, a crossover point is chosen randomly within a genus. So this is the chromosome 1, chromosome 2, and so on. You can choose the crossover point. That point may be any point. Let it be as a, you can represent as a 3, at 3 point or 2 point, somewhere. So you can position this from this point onwards. You want to perform the crossover. What you can do is the rest portions you can exchange, or sometimes what you will do is this portion you can exchange. Anything is you can do. Only what we are doing is a crossover point. Here, consider the crossover point to be as a 3. The crossover point is 3 means after 3 digits you can make a line. Or crossover point is 2 means you can make a line. Or 4 means you can make a line, like this. So after doing that, you can exchange that chromosomes. So parent 1 values will transfer to parent 2 values transfer to parent 3. Like that you can see. This is how we call it as offspring. How we are getting as offspring 1 and offspring 2. Offspring 1, this 2 will be exchanging, and remaining will be remains. 0, 0, 0 is remains. This is all three zeros will transfer. Lower side data will go to up, upper side data will come down. So that's what the remaining portion will not change, or any one side you can do. New offspring are added to the population. Now, the final one, before termination, there is a mutation also there. So, what is the mutation? In certain new offspring form, some of their genes can be subjected to mutation with low random probability. So, whenever as I mentioned, no, you select the PM, suppose probability is 5.5, let us assume that, and randomly if we select that value may be zero point 0.2, then low random probability, in that case you can change the particular genus value we are going to interchange randomly. That's what you can see. For that we have as a different types of mutation operators are there. Similarly, different types of crossover operators also there. After just different operators if I explain, after that I will go for as a topic, different types of crossover operators and different types of mutation operators explained. Here, flip bit mutation, Gaussian mutation, swap mutation. So here you can see randomly we select, this is going to be mutation happened because one is there, you replace with 0. 0 is there, replace with 1, like that. So this portion I want to do the mutation as per this logic I already explained in the previous slide. You can able to do the mutation. So one by one, these things I will explain after this. Now, finally, last sixth one. This is a sixth one. Termination. What is the termination? Algorithm terminates if the population has converged. What is the converged meaning? We will decide number of what you call it as the iteration. If that is reached, then automatically that is going to be terminated. Does not produce offspring which are significantly different from the previous generation. Then it is said that the genetic algorithm has provided a set of solutions to our problem. So now the process you can see we started an initialization and then compute the fitness. After fitness, if you marked as a iteration, this is the termination criteria. So first iteration, then it will go the parent selection, crossover, mutation, and then computation. And this loop will be repeated continuously. And once this criteria is reached, we can stop that. Like that, I have given different kind of model of flowchart. Everything is same, only the representations are different. As I shown today in the last previous slides, you can use that initialization. After that, the fitness, then go for as a selection, and then the crossover, mutation, and then we'll do the to call it as a termination criteria. Check if it is yes, then print the result. If it is no, repeat this to the from that point onwards. From the random selection onwards means the crossover mutation will repeat continue. So this is about the basic genetic operators. Now the next topic will move on to a different, because these two I am not explain in detail of these methods. This one also, crossover. We have different types of crossover: single point crossover, 2 point crossover, like that. We have different kind that I will explain. And after that, these mutations also I will explain. So that more or less, these are the different kinds of binary coded and then real coded, order coded crossovers. So these are all different types of crossovers I need to explain. So that we'll see in the next class. Any doubt you can ask me. Otherwise, you can leave. Monica, Sai Teja, only the attendees. Monica, roll number 2, Namma, Monica and Sai.
No, sir, six, sir.
6, yeah, 6. Sai Teja, okay. You can
Four
leave. Ma. Oh, yeah,
cited.
4. I will check.